So this is my experiment with the MOSFET that I'm having there, and this probably will answer some questions. What the hell I'm doing here? And maximum voltage is 32, 31.5, 36, and I'm powering with that 4.8 volts DC. Voltage peak to peak is usually the same as voltage maximum or very close to it, 37, while this is 36. Frequency, duty cycle, it doesn't show because it's very sporadic, it's very weird, but it is a duty cycle there. And yeah, that's important. Probably we can determine from the frequency the duty cycle, I'm not sure. For a second it showed something there a little bit. The thing is, and this is the waveform, which is very ugly. I actually got a very clean, for a second, waveform, very clean, without this intermittent little shits inside. So only like that, you know, very clean. But for some reason I try to modify here. I switch from here. By the way, it's 5 volts per division there, that's important. So I am getting this 5 volts here, a little bit more than 5 volts, probably like 7. But this spikes is what he is reading here. Hopefully I will not fuck up my oscilloscope. So here, if I'm switching this division voltage, this Vmax will top it at a certain value there, but it's not the real value. And probably this 5 volts that I'm having here is not the real value. Probably the spike is even more higher than what he can read. So that's the limit, probably, to not bust, to not fuck up to not damage the oscilloscope. So if I'm switching from here, so you see now it's 3 volts because it's the limit. It's an internal limit of the oscilloscope for security measure, for protection of the oscilloscope. So this is the waveform. It's having a ton of stuff inside, and I did actually try to move the potentiometer a tiny little bit left and right, just to see if I'm cleaning up that waveform, and it doesn't do anything. I can show you actually. So like I said, a tiny little bit like that, and it's doing absolutely nothing. And here. But it is changing, the waveform, it is changing, but it's not cleaning up all these little shits that you are seeing there. And when you see it like this, with voltage maximum 7 volts there, at 1 volt per division, you may believe this is on an okay graphic, an okay oscillogram, or an okay reading. But I believe the better way is to see it at 5 volts. And actually what I did, I switch it, my probe to 10 times. That is 10 times there. So right now it's showing this 7 volts maximum, fortunately, but the spikes, it doesn't catch the spike. That's why it's showing this voltage peak to peak 7, the same as the voltage maximum. You see, they are very close together. If this is 10 times, so if it's 10 times higher, so if right now we are having 5 volts per division there, so one division he thinks, the oscilloscope thinks, is 5 volts, but I turn the button on 10 times. So right now it's 10 times more than 5 volts. So this is 50 volts here per division, what we are seeing. The spike goes over that 50 volts. So it's about probably 60 or 70 volts, like that, spikes. This is very bad. Very bad. Why? Because, also, by the way, I was playing around. Actually, this should have been 12, but it moved like that. So this 12 volts, I'm varying the voltage for the driver of the MOSFET, that I'm having here, using this comparator LM393. So this is the driver for the MOSFET LM393. And right now I didn't specify it here. So right now it's exactly like here, 12 volts and 5 volts. But I didn't specify. So I specified that it's power supply 1, power supply unit 2. But I didn't specify what kind of power supply, because this was earlier test when I did it with this and with that, and it pulsed the hell out of that, because this power supply I link it here to this resistor, and then to this transistor, and to the ground, these 2 points, like you are seeing actually here, these 2 lines, these 2 power lines. So this is negative, that's positive, and that this positive is going like this through the transistor and to the negative rail. And like here, like with this transformer that I'm having, which is more safer for this kind of experiments, in my opinion at least, I'm afraid of this power supply to be damaged in some way, because probably I will show very quickly what it's doing. Let me show you what it's doing to this transformer. Let me show you the hearing. You cannot tell. Well, it's a very faint humming or buzzing. Now, when I'm changing this potentiometer, you will hear a change in sound. Let's hope my phone will catch that sound. So right now, right like that it did. And now I will turn it back. So this is the maximum here of the pot, like this. So now I will turn it back, and you can hear it. Yeah, it's a very, very faint sound, but it is there. It is vibrating a tiny bit. This transformer is very good, actually, very good, because it's very quiet, extremely quiet, especially for this kind of experiment. By the way, yeah, the resistor is getting warm, and my friend asked me how much warm is getting compared with the sun. No, usually when I'm making my experiments, everything temperature related, I'm comparing with the ambient temperature, not with the sun. And so this I can put my hands on, because I keep it quite a long time here on. So I will close everything and check the temperature a little bit, just to be sure. Yeah, this is very cold. This is cold. Yeah, it's cold. It's cold. It's very cold. And also on the chip, but this part should not get hit at all. But I'm checking anyway. This is warm-ish. So now this is my room temperature thermometer. Now it's 26.2 degrees Celsius in my room. So the ambient temperature is 26 degrees. Very close to 25 actually. Which is ideal temperature for making experiments like this. 25. Usually the rest of the year is 25 in my room. But this summer was crazy. This summer was crazy. I got 36 or 37 or 38 even. I don't remember exactly. But yeah, no, it was stupid hot. And I couldn't make I couldn't think straight because of that heat. Yeah, it was not nice. So I checked the temperature here, and it's fine. A little bit of thermic stress on this 50 watt resistor, 1 ohm resistor at 50 watt. If I'm putting larger resistance here, it will get hot or warm more slowly than this one, which is very low value. What else? Yes, I said that I will show you. So let me explain first of all the principle. What is doing actually? What this thing is doing? So my trusty knife. Let me use it to exemplify. So my probe, what I'm probing here actually, is here and here. So pretty much what I'm probing this 5 volts power supply, positive and negative leads. Is like I'm putting the oscilloscope here and here, but because the transistor is switching very rapidly, because of this driver that is doing it, is switching the gate of this MOSFET very quickly, the power supply itself is getting switched very rapidly. So pretty much this power supply is oscillating because of this transistor. We are getting an oscillation of the power supply and this is the reading that I'm getting on my oscilloscope there. So this is back at 12 volts there. I tested it with 10 volts actually for a very long time, and this, you catch me here at 12 volts, but usually I did it at 10 volts until now. Only when I'm filming I'm doing stupid mistakes. Yeah, you see how clean it is now. Let me switch the... Yeah, you see, very clean, very clean, or at least more. It was even more cleaner than this. Yeah, I don't know why. Probably it's because it's heating up something. So I switched from here the probe to one time, and it's showing me this. But this is not changed. The Vmax and voltage peak to peak is not changed at all. And yeah, let's continue. So this is the power supply that is switching here, and these spikes that we are seeing there are because it's exactly like an electromotor. Actually, I will stop it because I don't like my oscilloscope to read this high voltage. As you have seen, those spikes are because of the coil of the transformer. That it's when a coil is switched, is getting higher voltage, is basically is boosting. You know those buck converter and boost converter, and this is exactly the principle of a boost converter when you are switching a coil. And what I'm doing here is very close to a boost converter when you are boosting the voltage up, raising the voltage up. And probably in a well-designed boost converter, those spikes are more close one to each other, and it's designed for those spikes to be close to each other. But in my setup that I'm having here, they are very random. Like, and I have absolutely no protection. Probably the only protection that I'm having is this is this resistor here that is taking all the spikes on it, most probably, and is kind of protecting my oscilloscope input probably from that 70 volts that we deducted from that reading there. That's my theory, and this is the test that I'm doing here. It is strongly involving the power supply. This kind of test it is soliciting and is including the power supply as an active element in the circuit. Usually, power supply is a passive element that is not. It's only providing power and that's it. You don't consider it in the functionality of the circuit. You know, you put 5 volts or 12 volts or whatever, and the rest of the logic is done by the internal components that in your circuit. The power supply is just something external from your logic of the circuit. But here in this case, the power supply is part of the logic of this little small circuit that I'm having, and this was bugging me. This was a problem. I actually got very scared when I hear that sound, that high pitch sound from my power supply. The first test that I did it with this power supply. Let me repeat that test. Actually, let me get back to that experiment. The first experiment that I did before using this isolation transformer that I'm having here. This is a switch mode power supply what I'm having there, and this one as well. But this one will power this circuit here. I can power it from there as well, but it's more convenient because I'm having this alligator clips. Right now my oscilloscope is reading a waveform of 23 volts, peak to peak and maximum, at 50 hertz. So it is reading the waveform. Yeah, also the duty cycle is 32% there. It's reading something from this transformer, but it should not be like that at all. Why is like that? I have no idea. This circuit is not powered here. I closed that one, and only the transformer. I opened this transformer, so only. Let me show you like this. So all this circuit here, the driver is not powered at all, but this one is powered. This circuit here, the power supply, 1 ohm resistor and the MOSFET, and my probe is here connected, and here it's exactly like before. I didn't change anything. So right now is reading something through this turned off transistor, which is very weird. If I'm moving it here, probably it should change. Let's see. No, it's not changing. It's the same. Very, very weird. Probably it's some kind of leaking through the transistor, or my transistor is starting to get tired. Who knows? Who knows? And some leaking inside it is happening, and this is the waveform of some sort of leaking. Probably. Who knows? Who knows? Yeah. This is a new stuff for me. Absolutely new stuff. So let me set up the power supplies as I was experiencing before this setup that I'm having here. 1 second, please. Okay, now I plugged in this power supply here. So here to this circuit, like I had it before, and this power supply that you are seeing here is powering the driver circuit here. And this is the waveform. Let me check. Here is 1 time. Yes, it is set to 1 time there, like that. And here, yeah, when is on 5 volts per division, there is like there. Yeah, voltage, maximum voltage. Actually, I got 18 volts there, or 19 volts at some point. Is not catching those spikes all the time. That's why. And let me change. Now it's 2.5, and now it is 1 volt. But I don't remember this waveform. I didn't have it this clean, like it is right now. Before it was, I don't remember it. So this is 1 volt per division here. Usually it was catching more often that Vmax as 19 volts or something. And that's why I got scared. And do you hear it? The sound. And now, if I'm switching from this potentiometer a tiny little bit, like left and right, and if I'm changing the potentiometer, the amperage is changing, and the sound is changing. You can hear it. And I will not go more than this. This is the oscillogram. So now I will back it off. I hope you can hear the sound that is making. And when I made the readings with this oscilloscope, I swear to God, 19 volts, not like this right now, 6 volts. Very strange reading that I had before this test. Very strange. Okay, so because of those readings, yeah, you can probably see from time to time some spikes are visible there. I did catch them when I was not filming. Let me back down. Probably there'll be more. Yeah, unfortunately, it's not catching them probably. Motherfucker. Certain there. Yeah. Like this maybe. You see how high is that? Let me actually do the same trick here. I'll go to. So this is 10. Switch to 10 here. And let's see if this is 5 division here. Then 1 square is 50. And I don't see any kind of spikes. Yeah, I did see one. It was until here. So it's almost 50 volts. It's like a square here. It's like a little square. From this base to that point there is almost like a square high. So about 50 volts probably. Very Yeah. And it was more spiky than this. It was way more spiky than it is right now. Huh. Very, very, very strange. That I don't get the same result as I was getting before. Let me close everything and try it again, maybe to get nuts. No? This resistor is quite warm. It's very warm, towards getting hot. And now I'm checking the transistor, and it's very cold, very cold. So when I'm saying something is more warm or more hotter, I'm comparing it with the ambient temperature, that 26 degrees that we've read earlier. So now is probably a couple of degrees, but not that much. Like 5 degrees, maybe it's 35 probably degrees Celsius with my hand reading that I'm doing here. And another experiment that I did, I push up the voltage here to 10 volts, I believe. Like that. And now you can hear that sound. And when I'm switching from this potentiometer, pay attention to the sound and also to the amperage. And that's it. I will close it because I did this very quick experiment. Yeah, it is starting to get hot. That's very interesting details and I was facing with, you know, when I was testing at least this setup that I'm having here. Another very important thing, instead of all this circuitry that I'm having here, this is actually a MOSFET driver, what I'm having here, using this comparator. But you can use whatever driver you want. I actually purchased, somebody on the forums, a Russian guy suggested to me a PWM driver. It's a little board with a screen, and it's very interesting. It never occurred to me to search for such a device, and I did buy it. And my friend from America, he bought it too, as well. And this device is having 3 channels, and my hope is that I will get 3 PWMs per each channels, different, or whatever I'm setting them up to, whatever duty cycle. So theoretically, I can drive 3 MOSFETs, and those MOSFETs can drive 3 motors, whatever, or lamps, or, you know, as an example. It never occurred to me to search for such a thing. So, and now I'm having friends from Russia. From Russia. All right. Okay. Let me put back this old testing wiring and put back as it was in the beginning of the movie. All right. And we are back to those beautiful and very dangerous 70 watts spikes, which my oscilloscope is catching only 36. We are on 5 volts division here, and I cannot back it more down than it is right now. It should have been interesting to see a 10 volts or 20 volts to get more lower than this 5 volts here, or higher. Right now, I rewired everything as it was in the very beginning, so nothing has changed from the very beginning. I'm getting the exact same pulse that I'm having there, the same reading, very weird and shitty. The only difference is this 10 volts, before it was 12, but it's really not affecting anything there. And the MOSFET itself is, in its datasheet, is saying plus or minus 20 volts per gate. And I am willing to do that because I'm having sparing MOSFETs. But let's see, this is cold, and let's see if something will blow up live. Hopefully not. So right now I'm at 10 volts, and that's why I choose this variable power supply, because I can test with it very quickly this very cheap MOSFET driver that I built here. And it's very, very convenient to tweak it like this, you know, from this variable power supply. So right now, hold your shorts, because I'm going to the 20 volts. 14, 15. Let me film here if something will blow up to see exactly what. So now I'm 15, 19, 20. Okay. I'm smelling to see if something is heating up, like smelling hot iron, but no, not really. Should be exactly 20. Come on. Come on, you motherfucker. 20 volts. High amp is the mat. Like that. And here, the pulse didn't change at all. Yeah, it's still the same. Right now, theoretically, I'm driving this MOSFET very, very hard. And I should put it here and read the voltage gate probably. So now I'm probing. This white wire is directly to the gate. Yeah, okay, I can do it like this. So I'm probing the gate, and look at VPP and Vmax there on top, and here is 18 volts, and my power supply is leaving 20, and it's 2 volts dropping until it's reaching the gate pulse that I'm having there. The pulse here is very clean. This is what I like. This is good. This is very good, actually. It's a very good pulse, very clean. Well, cleaner. This is what I was expecting on the output on the drain when I was, where are you? Here on this reading, I was expecting something like this, clean like this. This is actually what I was expecting there, but shit. Right now, what I'm probing, where are you? Here, exactly here, where this squiggly line is. This is where I'm putting my probe, and of course, this negative lead is to the negative. So this are the 2 points that I'm testing. And yeah, I am actually delivering 20 volts, and let's see how hot it is. Yeah, it's not even warm. Probably I am warming it up with my body heat right now, but it is cold, very cold. Okay, I will back down to 10 volts because it's safer. To 10 volts, like that. And let's check this guy if he is okay. He is okay, just to be sure. Well, if something was wanted to blow up, it was already blown up already. I never did this 20 volts test on this driver for the gate. This is the first time live, and if something was having to blow up, was blowing up already. And theoretically, from the datasheet of the MOSFET, it says there 20 volts. So that's probably the best voltage to have to turn it on, fully turn it on. Right now at 10 volts, I'm not completely sure if it is fully turned on, because it's half of the datasheet specification voltage. The name of it is this guy here, IRFZ44N Mosfet at 94 watts, 55 volts, and 49 amperes. And this is the pin out there, and these are all the guys, 50 of them. I don't have 100. This is exactly 50 or a little bit less, like 48, because I screwed 1 or 2 of them. Let me actually put this back and continue reading and continue stressing my oscilloscope probes here with those spikes, which I'm very pleased that this oscilloscope is most probably handling those spikes somehow, because they are visibly more higher than the screen, and they are getting off the screen. Those spikes, it's clear, it's very clear. So what I was saying that before when I wasn't very accustomed with these transistors, with these MOSFETs, this particular MOSFETs, this IRFZ44N, and MOSFETs in general, because to be sincere, I didn't work that much with MOSFETs in my life. I did a couple of projects with them, but not that many that I'm a guru in MOSFETs. There are other gurus in MOSFETs, some other guys, but I am definitely not a guru. I am still learning them, and I'm trying to discover the best performance, the best way of driving them, and the best way to behave with them, how to use them the best way in your circuit. And this is my movie that I'm making right now, is trying to determine how to practically use them. And doing these tests that I'm doing here, I'm trying to stress them out probably to their limits, and try to make them run as the best as I can figure it out, because I am figuring it out alone, without any external help, because the guys that I'm talking with, they are giving me very extremely small hints what they think is the best way to drive it. The biggest hint and the biggest help I got with this circuit, this is not my circuit, this is my American friend circuit, is this PWM driver with a comparator, and it's the first time when I'm building a circuit with a comparator, specifically with a comparator. This is not an op-amp, this is a comparator, and this is the first time, and this was the biggest help that I got so far. But other than that, any kind of theory, how to reliably and to be sure, to be certain I'm driving a MOSFET absolutely by the letter, how they were designed by the factory or something like that. I never get that kind of knowledge. I have to guess a ton what to do and how to test them, and it is what I'm doing right now. I am solo, like a lonely wolf here, mostly. At least this is the feeling that I'm having. Although I am getting a tiny little bit of hints here and there from my friends, but from the forum, from the AAC forum, but they don't really tell me that much. They don't tell me do that, and you will obtain that result. You will obtain that graphic there. This is what I'm expecting from my friends. Yeah, black and white. Do that is good. Do that is bad, and you will fuck up something. Don't do it. And do this because this is good. This is how you explain. This is how you, if you know your stuff. Not that maybe no, it's wrong. One another thing that I did this test before I was used with these transistors. I was testing them at 5 volts all the time. Or most of the time. So like this, I was driving this MOSFET driving, this gate driving driver is pulsing here. Let me actually read it, and I'm probing it there. And yeah, you can see it exactly 5 volts. Exactly. Actually, voltage peak to peak is 5 volts, exactly 5 volts, which is good. It's very good. that's a negative number there. For some reason it's going into negative. So that's the 5 volts. And with this voltage on this, on the gate, exactly on the gate of the MOSFET is getting warm. And if I'm leaving it too much with this voltage, it will get very hot. I know from experience right now at this moment is, I believe it's starting to get warm, but it's still cold. Yeah, it's still cold. I don't feel it warming up. But usually I was getting them very warm, so I was stopping the experiment while I was driving them with 5 volts. So 5 volts is under voltage and is not letting them open fully. So the trick for the bottom line, or the idea for a MOSFET to be driven correctly, at least, to drive it at its probably at its maximum voltage from its datasheet. I might be wrong here, maybe a little bit less than that maximum that is specified in its datasheet. But from what I am understanding, the MOSFETs they must be powered. The gate of the MOSFET must have a very big voltage, very close to the one that is specified in the datasheet. If it's too big, it will destroy the MOSFET. And if it's like hundreds or thousands of volts, will destroy the gate of the MOSFET. And if it's too low, it's driving it is like underpowered. In a sense, it's stressing the MOSFET, and that's why it's heating up internally. In some circuits and some experiments that I did, I got the MOSFET very, very hot, driving it with 5 volts. But I might be mistaken. Maybe I was crazy with the MOSFET. I didn't put a safety resistor like this one here. I was driving it probably directly. Who knows? This was the objection that I got from AAC forums, from my friends from AAC forums, that driving it with less voltage potentially is weakening and potentially is destroying the MOSFET, is putting too much, the MOSFET is dissipating too much power at a lower voltage on its gate. That's the bottom line that I got from my friends there. So I learned my lesson, but there are situations like this one right now is not getting hot or even warmer. It's absolutely at the same temperature with the ambient, with my table. Maybe it's 1 degree warmer because I'm hitting it with my body heat here while fingering it. But yeah, in this specific setup is not getting warm or even hot, because I was getting if it was getting hot, I was getting out my digital thermometer and I was putting the probe on it to show you how hot it's getting. But right now it's not really necessary because it's not even warm, so it's very secured. It's very protected right now. Probably this one is getting, or something else from there. Who knows? By the way, this is not correct wiring for power testing. So here it is. This is thick cable for that I took it from a cord power supply. Actually, from this kind of cord that you are seeing here, which is quite thick. You see, is probably half an inch from my American friends, or like 1 centimeter, or 1.5 maybe centimeter, 1.5 centimeters. This diameter here, and the wiring are inside this kind of wiring, exactly this wiring, because I took exactly that cable, a piece of that cable that I got left, and I made this power cord, and with very big and hopefully better, alligators, and probably these probes are good enough. Who knows? But I should have used this power cable when I was powering with this device, this little power circuit that I'm having here. This is a little detail. I didn't get to actually drive that kind of power that will overheat the transistor, the MOSFET, or the load. At this stage that I am right now, I cannot efficiently and clearly calculate the power over the MOSFET. So I cannot collect a clear voltage from drain to source. That's the voltage that I want to extract, and from it, and also the current into the MOSFET from this wire, from this to calculate the power of the MOSFET itself. I didn't get to that point yet. With the setup that I'm having here, with this circuit that I'm having here, I'm kind of following the last experiment that I did with the NPN BJT transistor, this 2N3773. With this ones, if you remember, I was testing them, and I'm following the exact same idea. Well, the exact same. I'm following that idea when I was using those big transistors. But maybe this circuit is not the correct circuit or arrangement for collecting, to extract the power from this transistor, because I'm not getting clear readings. That's the problem. So this is my issue, and I had to think a lot about these problems that I'm exposing, very freely, very easy right now to understand. But I had to think quite a lot what I like and what I don't like, and what I need. Like this, I'm getting that voltage, maximum voltage, or peak-to-peak one. But I'm getting also, that's from the spikes, my impression, because it is right now is 5 volts peak to peak, and what I'm having there is actually like a 7 or 8 volts on this wave, and not that 36 that this is reading there. You see, it's changing, and also changing in the same time. Yeah, like I said before, the power supply is an active element in this circuitry that I'm having here. It's not a passive like in any other circuitry. So that's my, this is my interpretation, of course, and this is my logic, and this is my how I'm saying the situation is, at least with this circuitry. Probably I will need something more in this circuitry, what I'm having here, something on the drain source that can reliably and clearly catch a clearer waveform, and some filters for those noises, something to clear the pulse that I'm having there, something to make more readable all this garbage that I'm getting when I'm probing raw here. This is a raw probing, you know, brutal probing what I'm doing in this little circuit. I should have a more select and fancy way of reading it, something. This is my interpretation. So this side of circuit is doing its job. The waveform on the gate is very clean and very good, actually, exceptional. So I'm not talking about this circuit here. I'm talking only this guy, this line here, and whatever it should need next to it to clear out its oscillogram that I'm having there, its waveform, and to get a proper clearer reading. This is my interpretation, of course. This is how I'm seeing this circuitry and this experimentation that I'm doing here. So the conclusion is that I didn't manage to collect a true power reading over this specific MOSFET. I'm only relying on the overvoltage or spiking reading of this oscilloscope. He is doing his job, actually, and I truly believe him that he is doing his job correctly. But he is literally messed up by the some kind of interference between this coil here, and even that was which supposedly it should have been cleaner output. It's still interfering with it. This pulsatory frequency on-off output that I'm having here, or load, is like a big load, and I'm switching it all together, all in the same time, and I'm trying to collect the power dissipated everywhere, on this, and on this. So in these three elements. Theoretically, and I told this to my friend from America, and he was completely disagreeing with me because no, it's not correct, but I think it is. Or maybe if I'm mistaken, but for the moment, or currently, I don't have better ideas than this. So theoretically, the power that I'm getting from my power supply, which is this one, is not that anymore. But when I was testing with that, actually, when I was testing with this, and I was having it here and here, I was getting a current reading beside the voltage. I was getting the current. So that voltage times the current that was displaying, I believe it was 0.4 here, if I remember right, and here was 5 volts. So 5 times 0.4 is 2 watts per entire circuit, including itself, while it was pulsing, while the pulsing was happening. In this mode, what I'm having here, I cannot get any kind of reading, and that's why I'm saying I need something that is capable of reading, especially the amperage through here, that is going on when this is pulsing, when this line is pulsing here. So that's my actually this is the line here. This entire line is pulsing all the time. So this is the discussion. I hope I touched all the details. The reason that I'm using this transformer right now is to protect this power supply when I was having it connected here. Right now I'm having this motherfucker connected it here because I don't really care if he is damaged in some way from this pulsing. But I do care very much if my variable power supply that I'm having here is damaged or stressed and in some way, because I'm using it all the time. This little shit, I really don't care about it. It's great that it's doing its job. My bravo, good job that you're doing your job. But practically speaking, I do care more about that, to not fuck it up and not damage it, than this one. So that's why I changed it very quickly. I did very fast experiments with this one. I observed something is very wrong in the sound when I was listening to its sound that is creating from that very rapid pulsing, high frequency pulsing, and then I switched to this transformer, and I made a movie about it, the movie before this one, and how I constructed it. It's more an entertainment movie than a serious movie like this one. That's the reason why I'm using this kind of setup that you are seeing here. This is another point. This is another important point to mention. Yeah, let me show you my LM393 batch that I'm having. And here they are, LM393 comparator. This is not an op-amp. This is a new component for me because this is a digital component. It's not an analog like a normal op-amp is. So that's the difference. Where are you? Yeah, this LM358 op-amps. You see them here. these are analog reading, but this guy, this motherfucker, LM393 comparator is a, and I actually made a sign there that is a square wave. This is a digital, specifically made to digitally switch something, you know, and I believe my impression, my strong impression actually, and my strong belief why he used a comparator here in the first place and not an op-amp is because of the PWM to be a clear wave, a very sharp and clear and clean wave, and it was when I probe it there. Actually, I can show it again right now, and I'm probing it here like that. Well, this is a bit shitty because it's a very big, it's 5 volts per division there, and I will have to do it like 1 volt probably like that. Let's see. Yeah, and not even this one. Let me do it like. So this is 500 millivolts. That's the entire screen here, and it is a very clean waveform. It is a definite on and off. You know, it's a sharp switch on and switch off, and that's the idea of this. Why the engineer behind this circuit chose a comparator and not an analog op-amp. And this is my first encounter on my first circuit using a comparator, and I'm learning quite a lot from it, and I'm very happy that my friend from America, Mr. DL324, he put me to use it. Originally I had 2 scrapped ones. Actually this is the original one that I use, and it's a scrapped comparator, and I had it in my list, in my text file on my PC, and I had it there, and he probably saw it there because he is having my list, I hope. And he constructed this circuit with the components that I'm having, and I'm very grateful to him because he knows this little detail about me, that I'm building stuff with the components that I'm having and that I can purchase if the needs be. Yeah, this is already a very long movie, and I didn't do much here as result wise, but I did a lot of testing wise, and even if I'm not getting a clear power reading from this MOSFET, I did figure out a couple of problems with this kind of circuitry that I'm having here, and I think it's good enough for the moment, but I really need, my target is to actually read the power of a MOSFET, and currently right now I cannot do it with the stuff that I'm with the ways I can read here. I cannot do it in these circumstances with the tools that I'm having here. It's impossible. So we have to think about something more smarter for me to be able to read this kind of stuff. All right, that's it for today. Thank you very much for everything, and thank you to my friends, especially to my American friend Mr. DL324, to my other friend from England, from UK, you know who you are, and also from Germany, a friend W. R. Brown or something, a guy from Poland, I believe, he participated also, and 2 guys from Russia, one worse than the other, worse and mean. Those guys are not people guys, definitely, but they are very knowledgeable about electronics, and they're very good in their side of electronics. But for some reason, I'm not their friend, and they clearly mark this specific and mark it very strongly actually, that I'm not really their friend. They don't want this kind of friends like I am, this experimental friends. They want better knowledgeable probably, or more engineer type of, and more successful, not an artist that is not getting a salary for 11 years like I am, because of Romanian capitalism, which is striving for others, not for me. But yeah, everything will end soon enough. Nothing lasts forever, you know. So make friends when you can, you know, if you can, with who you can, because that's important, I believe. This is my philosophy, my personal philosophy. Make friends when you can and with who you can, and try to make as many as you can, because having friends is very good. This is a very old, from a very young age, philosophy of life for me. All right, enough of philosophy of life. Thank you very much for watching. Thank you very much for understanding what I'm doing here, and I hope I can reach that kind of point where I can clearly point, yes, this is the power that a MOSFET is supporting. This is the value of the power dropped on this specific component, and even the load power, to be certain, absolutely clear and visible. Yes, this is it. This is what is the power value, and this is what is the power value for this one, and combined is total power, you know, from the power supply. And we will see in the future if I will be able to reach that point. I hope I will, but when I don't like something, I'm kind of too direct. I'm saying it. I don't like it. I don't like this, or I like this, and you know, it's good. Yeah. So another important detail is that I'm using all this time on this circuit, and here I'm using this 4.8 volts DC here, but I didn't use this 9 volts one. And this was the reason I restored this transformer that you are seeing here from that pitiful state that it was before restoring. And because of this 10 volts, 9.7 volts that I'm having right there, this is a weak testing voltage what I'm having here, but here is a more power, or actually is full power testing of this transformer and the circuit that I'm conducting the experiment here. So at full power from this power supply, is this. Right now I'm at half of it using it. So this is another very important thing that I didn't get into making the experiment with this full power transformer, to use it at full power pretty much, you know, here using this module. But right now I'm using only half power from what he can deliver, and is weaker, if it's half, is weaker over these two elements pretty much. And this is another very important detail to mention about this setup that I'm conducting right now there. All right. Another very important detail, and I did a lot of tests with this setup that I'm showing you here. You see here is an erased line, and there is a value probably for that resistor. But I was not having this two power supplies different here when I started this experimentation. I was having only one power supply, and I was connecting it like this. So eliminate this. I will actually show the actual circuit. And with a single power supply that is powering both the driver and the load mechanism that I'm having here, I was getting way more erroneous results than when I'm using two power supplies like I'm having here. And I spent a lot of time with that circuit that was using one single power supply for both sides. And I couldn't understand too quickly why I was having the problems that I was having. And I was having some very strange and serious problems, and I couldn't figure out why I was having it there. But now, with two power supplies, it's I kind of split the problems and leave the problems mostly here, and protected with this power supply. I'm protecting this side of the circuit. So that's the difference, and that's the history, and that's what I was having to deal with. And actually, my friend suggested to me to use two power supplies. My friend from America, my American friend, he suggested to use two power supplies, and I did it, but very late. I was trying too hard to make it work from one single power supply, and I couldn't. I was getting all sort of very strange, bizarre, unorthodox errors, and everything was influenced. This side of circuit probably was influencing the driver circuit and not driving it correctly. And the power MOSFET was getting very hot very quickly, actually, extremely quickly. In the very beginning, I didn't even use this one resistor, 1 ohm resistor at 50 watts. I used directly the direct power that was coming from the same source, from one single power supply, was getting here, and that overheated the MOSFET fantastically hot and fantastically fast and hot. And I did in a fraction of a second, actually. It's very quickly. In 1 second, it was already 100 degrees or even more. My skin was boiling over that transistor. So this is quite a stressed transistor what I'm having here. Unfortunately, it's a little bit stressed. I don't think it's totally damaged or broken. I believe it's still good. Like 95% good, I want to say. Even if it got hot, very hot. But if you look in its datasheet, you can push it to, I don't remember what, 170 degrees Celsius, I believe. Yeah. So that's part of the history and part of the bad experimentation that I did until reaching this stage when I'm using two power supplies and I'm dividing the problem basically. And now it's more obvious what the hell is going on. It's more obvious for me that this power supply is becoming an active element in this circuit because of those pulsings that are happening because of this transistor. And my little description that I made here is not even covering the entire range of experimentation that I did when it was having one single power supply. Because of how many errors I was having, I was very undecided to do any kind of movie about it. And now I may say I'm having quite a brighter range of results with two power supplies. But back then I was having so many bad results, and I cannot cover. It's impossible to cover them all here. But they were tens of problems. And I had to sort them out and figure out what the hell is going on. If I remember right, my power supply got to 5 amps at some point. 5 amperes when I was switching from this potentiometer. Probably that was the case back then. Here, this one, back to the so right now it's pointing here at this point, but when I was rotating it to point in this side, I got a ton of bad problems, very bad problems. I had a ton of them, and I'm not even it's impossible to cover everything right now, but I'm telling you, it was a very big deal back then to figure out and to split the problems that I was having. And see you later, and goodbye from your favorite artist electronics, Mr. Q12. And I hope it helped someone that is watching these movies as well. Bye bye from your favorite artist electronics, Mr. Q12.